Hello everyone, I hope you guys are doing good and studying well. Well, in the last video, I've discussed about the field due to a ring and we have seen some questions based on that. Today we're going to be talking about the straight line, the line having charges, a linear charge density. We're going to be talking about that. We're going to be talking about the field because of an infinite line, because of finite line, and we can see about the semi-infinite lines, and we're going to see some mixed problem on that, right? It's very important to understand the derivative of these kind of questions, because derivative is a process of understanding the concept. A lot of people ask me like in these competitive exams we don't need to know the derivative, but guys, if you know the derivative properly and if the question is a bit twisted, you will be able to do that. You just rely on the final outcome, then in some questions which will be twisted, you're probably gonna lag over there. So make sure you understand the process, and by any chance if you forget the formula or something, you will be having this basic strength of deriving things over there then and there itself. So it's very important to understand the process of coming to a result. Fair enough? Alright, then let's start. As you might have seen the headings, electric field due to straight line. It's going to be finite, it could be infinite as well. Now let's say, for example, I have a straight line, straight wire. As of now, okay, let's say some length, some finite length, having a charge density of lambda coulomb per meter. Well, the lambda is the linear charge density. Alright, then let's say I want to know the field at this particular point P at a distance of, let's say, D from this straight wire. Okay, so I have not kept it at the middle point. It's not like that it has been kept at equal distance from these two terminals. No, it's not. Let's assume it's a distance D. Now the process is going to be same. I'm going to find small element on this wire. We're going to find the small field at this point because of that small particle, and then since electric field is a vector quantity, I'm going to find the components, and then probably we're going to go and integrate that. So idea is very simple. Understand this entire process. We choose, these are the extended bodies, right? We choose a small particle and then we work on that. I have explained this process in the previous videos. If you have not seen those videos, go and watch it out. Well, what I've done, a lot many text will see the field because of the wire, because of a ring, and then the questions based on that. What I have done over here, in the previous video I have kept one video specifically for the ring. Now today's I'm going to be talking about the straight line. So I'll be doing the questions on this only. So I have segregated the particles in one lectures. Alright, then fair enough. So what I'm going to do now, guys, I'm going to choose a small element over here. Let's say some small element of length dl at a distance of, let's say, L from this point. The distance of this elementary particle from this point is going to be this, and the field, let's say small de, is in this direction. Let's say this is D, this is L, then this distance would be L square plus D square under square root. Now let's get back, come to the its distribution along its components. Well, let's assume this is theta, then I'm going to have one field in this direction and one field in this direction. If it is theta, this angle going to be theta. Well, then this is going to be dE cos theta, and this part is going to be d sin theta. So what we, basically in this kind of things, we have given this name, we have assigned a name. Let's say this is E perpendicular. Perpendicular means to the wire in this direction, so that's why we say it's perpendicular. And this is normally called as E parallel, that is parallel to the wire having charge. Alright, let's say we have a positive Q, let's say plus Q over here on this wire, and the linear charge density is lambda per coulomb. So idea is very simple. I'm going to find the value of dE, I'm going to find the value of dE cos theta, I'm going to find the value of dE sin theta. So basically I'm going to get the perpendicular field and the parallel field. Let's do that first, and then we're going to discuss more about those things in depth. Alright, then let's talk about E perpendicular. Okay, E perpendicular should be nothing but your dE cos theta. In this case, we need a little bit concept of integration. I'm sure you guys are done with that. If not, don't worry, I will be helping you with that as well. Now dE, it should be K dq. Dq should be how much? Lambda times dl. if I write dq over here, dq should be lambda times dl. Alright, I'm going to have lambda times dl over r square. R square is this part. I'm going to have L square plus D square. The root of that will be eliminated because of the square factor. Now cos theta. So cos theta should be how much? D over this part. So the cos theta is going to be D over your L square plus D square to the power of 1 by 2. So this is your E perpendicular, small part of that. Alright then, let's do some simplifications over here. I'll be having K lambda D dl, because D is a constant, right? It is not a variable over here. K lambda D dl, and denominator will be having L square plus D square to the power of 3 by 2. Now if I want to know the E perpendicular, okay, let me put the integration over here. So E perpendicular should be integration of this. Now the problem comes with the defining the limits. Let's do one thing. Over here we can see that L is variable, right? Because L can go from here to here, or probably to this, to the bottom side, and the derivative is in terms of dl. Now if I change this elementary particle from here to here, this length will also change, right? And this angle will also change. What we can do over here, we can get this thing in terms of theta, because that's going to make your life more easier in doing calculations and in solving problems. So if you have this kind of thing, I'm sure you guys remember in integration, what we can do in this case, we can choose L is a variable. Let's say L is equals to, let's say L equals to d tan theta, right? Because tan theta is going to be how much? L by d. So L should be how much? D tan theta. Now if I differentiate this, dl by d theta, because now if I'm putting it in theta, theta becomes the variable, right? If I change the inclination of this thing, that's going to be changing in the value of theta. So let's say theta is a variable now, because I'm writing L in terms of a constant d and a variable theta. So my entire focus should be shifted towards change in theta, and that's going to help us in deciding the limits. Okay, so pay attention over here. So dl by d theta should be d times of secant square theta. It means dl should be d secant square theta d theta. Okay, I've reached till here. Now let's start replacing the value of L in terms of d. Let's see what we get over here. Let me use the different color. So E perpendicular should be, let's keep the constants out, k lambda d. Integration, if L is d tan theta, this part is going to be how much? D square tan square theta. If I take out d square common with this power, it's going to be dq. In denominator I'll be having dq. 1 plus tan square theta is nothing but secant square theta, and secant square theta to the power of 3 by 2 is going to be secant cube theta. You can just pause the video and you can do it if you're getting any sort of trouble in this. Now dl is how much? D secant square theta d theta. We have reached till certain simplified state. It's pretty hard. Okay, now if I do the cancellations over here, and okay, let me just keep this d inside as of now. So I'll be having d square. So this will cancel. I'll be having d, so I can just keep it out. I'm going to have k lambda over d integration of secant square theta by sec cube theta. I'm going to have 1 by sec theta, which becomes cos theta d theta. Now I'm going to set the limit of theta. Now let us have a look at this thing. So if it is a finite rod, let's say, then the variations of theta could be seen this way. Now we have to be slightly careful over here, and we're going to use the same notation for the entire problems for the entire time. Let's say, normally I have seen a lot of people getting students asking me how to choose theta and what should be the nature of theta in terms of sine. Okay, what do? I take this mean position, the distance at the mean position. One angle with this extreme would be measured, let's say this direction, then this should be measured in this direction. You can choose to take this as a positive, clockwise positive, or anti-clockwise positive, makes no difference at the end. Alright, so let's say I'm choosing this angle as theta 1 and this angle is theta 2. This entire angle theta 2, the blue color, and this is theta 2. I'm going to choose one part as negative, clockwise and anti-clockwise. Make sure you keep that in mind. Now the limit, let's say how the limit is changing. The limit should be changing from theta 1 to theta 2 for the entire set of rod, right? Since I have taken this as a counterclockwise, anti-clockwise, let me choose this is negative theta 1 to positive theta 1. Always the angle is chosen from the line joining. You can make that a standard way of solving the question, and stick to the same thing for the entire questions on this category. Do not divert. This is going to give you result correctly in all the cases. So take the main position, this line, and choose the angle accordingly, negative and positive. I'll be solving quite some questions on this. As of now, just keep this in mind. I'm sure you guys are okay with this, negative theta 1 to positive theta 2. The integration of cos theta is nothing but sine theta. That should be k lambda by d sine theta. The limit should be negative theta 1 to theta 2. So I'm going to get sine theta 2 minus of minus sine theta 1. We know that you should know that sine of minus theta is nothing but minus sine theta. That's the mathematical rule. So let me write it over here. You guys can check it out over here. Then the electric field E perpendicular should be k lambda over d times of sine of theta 2 plus sine of theta 2 plus sine of theta 1. And that is one of the component of the electric field. So we have actually found out this part. Fair enough, guys? Just note it down. And in this, if you have any sort of queries or questions, I would be happy to help you. Let me know through the comment box. Okay. Now we're going to be finding the parallel component, that is d sine theta. Fair enough? Okay. Let me quickly erase this. So the next part is to find the parallel component, and there is one thing that we need to understand, in which direction the parallel component will go. Well, it should be in the net. Will it be in this direction or will it be in that direction? We're going to discuss about that. As of now, you can see that I have chosen this direction, just a random selections I've done over here. I'll be discussing more on that as well. Well, E parallel should be integration of dE sine theta, right? Now let us put the values over here very quickly. dE should be how much? K lambda dl over will be having your L square plus d square sine theta. Will be, in this case, sine theta will be how much? Sine theta is going to be L over that length, right? It's going to be L over L square plus d square to the power of 3 by 2. No problem. Let's have the integration sign over there. So I'm going to get k lambda outside. Well, L is variable, I can just take it out. So I'm going to have something like this, L dl over L square plus d square to the power of 3 by 2. I'm going to do the same thing. I would try to get the variables in terms of theta from this variable differentiative dl. Alright guys, so I know that. Let's say L equals d tan theta. That's what we have been doing. So we know that dl is going to be d secant square theta d theta. Alright, I'm going to use this over here. So if I substitute it over here, I'll be having k lambda. L should be d tan theta. Let me put d tan theta. That should be d tan theta. Denominator, the same process. L is going to be d square tan square theta. I'm writing it right away. It's going to be dq secant cube theta. Now let's talk about dl. dl should be d secant square theta d theta. Let's put the integration. Well, d square will be cancelling and giving you 1 by d. So I'm going to have k lambda integration 1 over d. I can keep it out. Tan secant square sec cube. We're going to give you sec theta. Tan by sec theta is nothing but sine theta. So I'll be having sine of theta d theta. limit same thing, negative theta 1 to theta 2. Well, integration of sine theta is negative cos theta. I can write k lambda over d times of cos theta. I took this negative out, negative theta 1 to theta 2. I'm gonna get k lambda over d cos of theta 2. Now minus of cos theta 1, that becomes minus of cos theta 1 with a negative sign outside. So if I take this negative inside, I'm gonna have, let me erase a bit of space at the top. So okay, so at the top, if I just put it inside, so E parallel should be k lambda by d. I'm going to have cos of theta 1 minus cos of theta 2. So that is your parallel electric field. Well, generally we should take theta 1 as the smaller value, but that's okay. It does not matter, but it's probably going to help you in the calculations. I'm going to set a standard way of doing that. As of now, what I want from all of you guys to write this E parallel and E perpendicular in one part of your notebook. Write down k lambda, and you should be remembering it. Sine of theta 1 plus sine of theta 2. So this is very important result, guys. Now, as I told you in the very beginning, we should know this entire process in order to solve some really good questions. All okay, guys? Note it down. Meanwhile, I'm going to clean it up, and then we're going to see the next way of doing it. I'm like some other part of that. Okay, E parallel, I'm going to quickly recall. E perpendicular is going to be k lambda by d sine theta plus 1 plus sine theta 2, and E parallel should be k lambda by d cos of theta 1 minus cos of theta 2. Just remember this. And how to remember? By solving more and more questions. Okay, so let us solve some more questions. Alright then, now we know that. Let me just quickly write those two results over there. E perpendicular should be k lambda over d, which is the distance of the point, over sine of theta 1 plus sine of theta 2, and your E parallel should be k lambda by d cos of theta 1 minus cos of theta 2. Okay. Now let's just choose a random thing. Let's say I have, this is my wire. Normally I choose, this is my, let's say, theta 1 and theta 2. I'm keeping this convention. You can go with the theta 2 and theta 1. Other way makes no difference. Trust me. Okay. Now, having said this, let us, as I told you in the very beginning, try to choose theta 1 the small one, and then probably, we can go ahead. Even if you don't choose theta 1 as a smaller angle, any specific angle, it is not going to affect the result. Alright. Now, let's say for example, how to choose this angle and all. Let's say if I have this wire over here, and at this point I want to know the electric field. Let's say this angle, these angles I'm giving you. This distance is d. Lambda coulomb per meter is the charge density on this rod. Let's say this angle is 40 degree and this angle is 20 degree. Okay, I'll be having some E perpendicular in this direction. Now the fact is how to decide in which direction we'll be having the parallel component. Now let us understand this properly. I know that this part is shorter than this part because of the angles differences. Okay, let's say equal to this. Let's suppose this length is x, for example. So this part is going to be x. Fair enough. Now it means because of this, they're going to be filled in this direction. Let's say I'm choosing DE1 or DE because of this. A part of it will be going in that, and part of this would be coming in this, right? Sine component DE, let's say DE sine theta, sine 20 over here. Because of this, one part is going to be in the top, another is going to be in this direction, right? Now let me use the black color for that. Because of this, let's say this is my DE2, this is, let's say, DE1. A part of it, theta 2, let's say assume theta, that is theta 2, okay, and part of that this should be DE sine of theta 2. Let us choose theta 2. I have no problem with this. Let's say this is theta 1, and let's say theta 2, theta this is going to be 1 over here. Let's understand this properly. Now I'm sure that this value is going to be greater than this value, right? That's for sure. So a part of it, let's say from here, the field due to this part and this part will be countering on these two horizontal direction. What I mean to say, the electric field because of this in this horizontal direction is d sine theta. Okay, and because of this also will be having some part of it, so those two will get nullified, right? But the electric field because of this remaining part will be still existing in this side, isn't it? You understanding my point? So the electric field by this extra element, I would say, will be existing in this side. So the bottom line is we'll be having E perpendicular in this direction and we're going to be having E parallel in this direction. So E parallel should be in this direction. Forget all this stuff now, as we've already discussed. So E perpendicular is going to be in this direction and E parallel is going to be in this direction. All right, we have discussed because this extra element. So that is the way we choose to understand the direction of the E parallel. E perpendicular is very clear. It's going to be just perpendicular to the lines having charge, but the E parallel will be opposite to, in the parallel opposite to the extra element, that is opposite to the bigger angle. All right, now if I talk about this part E perpendicular, it's not affected by whichever angle you choose over here, you know, theta 1 theta 2 doesn't matter over there. In this case also it will not matter, but normally if you choose theta 1 a smaller value, that's going to be great. So for this theta 1, let's say choose 20 degree sorry, theta 1 is 20 degree and theta 2 is 40 degree. Fair enough. So that is the way in which we decide the direction of parallel component of the electric field. Now one more thing, over there the point joining the particle and the line was coming in between these two extreme points, right? There could be the cases in which the line joining the point at which we have to find the electric field and the line of the charges line might come out of the line, right? So let's see in those cases what we get to do. All right, let's see how to decide the angle. That's very important, guys. Just be attentive. Okay, let's say if I have, let's say, a wire like this having a charge density, let's say lambda coulomb per meter, and my point where I want to find the electric field is here. Okay, now somewhat like this. So if I join these, let's say it's making some angle, and let me join this. So you can see that the perpendicular distance d from the line is coming out of the line of the charge, right? So let's say this angle is probably 30 degree, and let's say this angle probably you can choose maybe 10 or 20, let's say 20 degree. Now let's see how to decide the angle over here. Now as I told in the very first part, you know, in the beginning, that we choose the angle with this line, right? So theta 1, if I want to know theta 1, it could be theta 2 also. Let me try to find the angle which this line joining this point charge and the wire makes with the top extreme. That should be how much? 30 plus 20, 50 degree. So theta 1 should be how much? 50 degree. So what I've done, I've taken the angle in this direction. Okay, so now theta 2 should be from here in opposite direction, because in derivation I have chosen the limit from negative theta 1 to positive theta 2. Okay, and by doing that, when I was doing that, I've chosen the angle one in clockwise, other in anti-clockwise. I'm gonna stick to that. So the angle between this line joining the wire and the point at which we have to find the field and the second extreme point, that should be this angle. If you guys are okay with this, let me know in the comment box. So that's going to be the angle, right? Well, so theta 2 should be how much? 340 degree, or you can choose to be, take it to be negative 20 degree. Understood this part? Negative means this side. So in the beginning you can rewind back and check that I have chosen the angle one clockwise and anti-clockwise. That actually decide the nature of the angle, right? I think that's a major problem which people face, students normally face, that how to decide the angle. So I'm sure it's clear to all of you, right? Let's see one more example like this. Chalo, let's suppose ki if I'm doing it here. All right then. Let's say this is the wire. Okay, let me just erase this part. Okay, just a second, people. Okay, now let's say the point is here. Okay, and let's say this extreme will be joining here. Okay, let's keep the same value, doesn't matter, 30 degree over here. Okay, and that should be the perpendicular line with this thing. Let's say this is 40 degree. Okay, with one extreme, let's say this is theta 1, so theta 1 should be how much? With this extreme, it should be how much? 30 degree plus 40 degree, 70 degree. Okay, it became a little bit messy. Theta 2, same perspective, 70 degree. How did you find it? This way, right? So the theta 2 should be, I'm going to start from here and I'm going to come back like this, somewhat like this, isn't it? So theta 2 should be 320 degree, or it could be equals to negative 40 degree. So that is how we have to choose the angle. Keep this in mind. You can probably go back and just check this thing one more time, just to have the clarity on the ways we choose the angle. So make sure you choose one angle, all the angles from the distance, the line joining the point and the wire, one clockwise, one anti-clockwise, things will be taken care properly. Okay, having said that, let's do some numerical using this concept of angle selection and some standard way of some standard question. Actually, I'm going to keep this on the board for your reference, so that while doing every problem you guys will have sort of a visuality to the formula over here. Let's say I have a semi-infinite wire, or let's say finite wire, infinite wire, infinite wire. Let's see what's happened in that case. So far we have spoken about a finite wire. Let's see what happens when we have the infinite wire. Okay, so let's say if I have the infinite wire like this, and there is a point P at a distance of d, the charge density is lambda coulomb per meter. I just want to know the electric field at this point, let's say P, due to this infinite wire having a charge density of lambda coulomb per meter. Okay, I'm gonna have E perpendicular. Since both the sides are equal, I can choose any direction. For now, I know they're gonna just subside each other, but let's say E parallel having in this direction, doesn't matter to me. E parallel, sorry. So E perpendicular should be how much? K lambda by d sine of theta 1. Well guys, theta 1, as we know that if I take this to infinity, understand this part, infinity is a very relative term. For me, let's say if I just get stick, probably if I look at my hand, if it's this, I can see the top and the bottom of my hand, right? If I bring it damn close to my eyes, I would not be able to see this tip of the finger, right? Though it's a very finite length, still I could not see. The moment I became close, my eyes became closer to this, right? You can see that. So the infinity is a relative term, and it depends upon the distance, right? Now let's say if it's damn close to me, I can see that this angle should be how much? 90 degree, because I cannot see the top of that. The angle should be how much? 90 degree between the eyes, the lane, the straight side from the eyes and the top part of my finger. So this angle should be 90 degree, right? Fair enough. So you should know that infinity is a relative term. If I just look at this wall, I can see the top and the bottom of the wall, but if I just get damn close to the wall, looking at the side, I would not be able to see the top part of the wall, right? Though it's very much finite, probably 12 to 13 feet, that's all. But now that also became infinite to me, because I cannot see that, visual was not there. So relativity is a infinity, infinity is a relative term that depends upon this distance. If this is kind of quite far away, but still if this wire is too big, again that's going to be infinity. Now if it is infinity, the angle should be how much? 90 degree. So I can say that theta 1 in this case should be 90 degree, and theta 2 as well should be how much? 90 degree. Fair enough? Alright then. So what I'm going to get now over here, I don't have to choose minus 90 over here, because already we have done that in that question, isn't it? Okay, now so k lambda by d should be sine of theta 1 sine 90 degree plus sine 90 degree. So you can see that sine 90 is 1 plus 1 2. I'll be having 2 k lambda over d. That is the E perpendicular. Now let us try and find out the E parallel component of that. Alright, so if you look at the E parallel, you have the formula right over there. That should be k lambda over d Cos of 90 is 0 minus cos 90 is 0. So I'm going to have how much? 0. And that's quite logical. We have equal parts to the up and to the down, the parallel component is going to be nullified. So that is the formula for the electric field due to an infinite wire having a charge density of lambda. Well guys, that could be negative lambda also. So make sure you do put that lambda with the sign itself. It could be 2, it could be minus 2 also. Well, so you have to remember this, keep this in mind. This is very, very important. You get to keep this in mind because we'll be using it in questions to solve it. All right. Now let's see the next case when the lines are, let's say, semi-finite. Semi-infinite, I would say, not semi-finite. That's a better word. Let's see what's going to happen when the lines are semi-infinite. All right. Now the next part, semi-infinite. Semi-infinite means it's going to be infinity tending to infinity from one side and the other side should be fixed. Okay, so let's have a line like this, charge, so this is over here and I want to know the field at this point, let's say at D point P. This is going till infinity. The charge density is lambda coulomb per meter. I want to know the electric field at point P due to this wire. All okay? In this case, we're going to be having perpendicular as well as parallel component because we do not have equal and opposite length over here to subside the parallel component to the electric field. Okay, no problem. So let us try and do E perpendicular. That's going to be how much? K lambda over D sine theta 1. You can choose to have theta 1 up, down. It's all your wish. Let's say this is theta 1. Well, theta 1 should be 90 degree. So I'm going to have sine of 90 degree plus theta 2 is 0, right? From this extreme, what is the angle made by this line joining this point and the straight wire? That is 0 degree. So I'm going to have sine of 0 degree. Well, that should be how much? K lambda D, and that's all. So electric field perpendicular part of that because of straight semi-infinite wire, that should be how much? E lambda K lambda by D. Now let's talk about the E parallel part of that. That should be again K lambda by D times of cos of theta 1. Okay, let's 90. Cos 90 is how much? Minus cos of theta 2 cos 0 degree. I'm going to have K lambda D is 0 minus 1. Okay, so I'm going to have K lambda by D. Okay, the negative sign shows it's going downward. Not a problem. The negative sign shows that I have chosen a bigger angle as is smaller, as theta 1. Normally I have told you that choose a smaller angle. So if I have chosen, let's say, smaller angle, cos 0 degree, that would have made my life more easier. Cos 90, I would have got how much? 1 minus 0. I would have got how much? K lambda by D. So certain things gonna keep your life easy. Don't get confused at why it's negative. Just the direction. That's all. Nothing much over there. Okay. Now let's try and make some more questions on this. Okay. Let's try and put a point probably at equidistance from the wire which is bent in the L shaped. Let's say, for example, I have an infinite wire, semi-infinite. Okay, let's say these are the semi-infinite wire coming over here, and this is also a semi-infinite wire. Okay, so this is a semi-infinite wire. Okay, having a charge density of lambda coulomb per meter, and you also have lambda coulomb per meter. Let's say I have a point P which is at distance of, let's say, D from here, and let's assume D from here as well. So this is my point P at which I have to find the electric field. So the question is, find electric field at P. I would like you guys to pause the video and try it by your own, and then you can discuss this together. All okay? Fair enough. Now let's see. In this case, let us talk about the electric field by this wire first, and then we can talk about the electric field by this wire. Because of this wire, we'll be having a component that's E perpendicular in this direction, and E parallel, it's an infinity, right? So I'm sure you guys will agree that the parallel component should be towards left, isn't it? Because this side we have plenty of length to counter this part of the length. So the electric field parallel should be in this direction. So let's say this is E parallel. So the blue color I'm using for this wire. All right. Now let me use the probably the red color for this wire. The electric field, the perpendicular by this wire, should be in this direction. Okay, and the parallel should be in this direction, isn't it? That should be E parallel. So I'm using the red color for this wire and the blue color for this wire. Now let us try and find the E net in, let's say, parallel. That is because of these two. All right then. So E net in this side, E parallel should be, let's say in this direction should be, or probably you can just go ahead and check E parallel minus E1. You can do that, no problem with that. So it should be, let's say, E parallel minus E perpendicular. Now this E parallel, because this semi-infinite wire, just now we have done, right? E parallel due to semi-infinite wire should be how much? We just now found that, and E perpendicular also, but there is a distance d over here. It's not at the end point of semi-infinite wire. No problem. Let us try to find the angle now, because that's more important over here, to find this angle. Okay, distance is d, this is also d, so this angle should be how much? 45 degree. Okay, if it is 45, even this is going to be how much? 45. Fair enough. Now if I want to know this part, E parallel, the blue one, so that should be because of this wire. So let me join, this is going to be 90 degree. Okay, so E parallel should be how much? K lambda. What is the distance? D itself, D. Now cos theta 1, choose a small angle, cos 45, I'm writing it here, cos 45 minus cos of 90 degree. I'm sure you guys have agreed with this thing, this part, okay, because this wire, E parallel, K lambda by D, cos of 45 minus cos of 90, minus E perpendicular, and this E perpendicular is because of this wire, right? So in this case again, this angle should also be how much? 45 degree, no problem. That should be K lambda by D, and that is perpendicular part, right? Because of this wire, that is sin theta 1 plus sin theta 2. So sine of 45 degree, sine 45 degree, theta 2 should be how much? 90 degree, right? Sine of 90 degree. I'm sure that should not be a problem to all of you. Now the rest part is simplification. Okay, I'm going to take K lambda by D common. Let's say cos 45 is how much? 1 by root 2. Cos 90 is 0, forget it, minus sin 45 is how much? 1 by root 2. And sin 90 is how much? 1 minus 1. I'm going to have K lambda by D times minus 1, because these two will be cancelled, right? So let's say minus means towards left. That's not a problem over here. Okay, so now let's talk about this part. Let's talk about the vertical part this time. E net in the perpendicular direction, this part. Well, I can choose to have this minus this. Okay, so basically this negative sign indicates that it should be in this direction. That's what it means. So that should not be a problem to all of you guys. Okay, now E net in this perpendicular, that should be how much? E, this perpendicular, let's say, minus E parallel. Fair enough. Okay, now E perpendicular is because of this wire, right? So E perpendicular should be how much? K lambda over D sine of 45 plus sine 90. I'm writing it right away this time. Sine 45 plus sine 90. Well, that should be 1 by root 2 plus 1. Okay, minus E parallel K lambda by D, and E parallel will be because of this wire. That should be cos of 45 1 by root 2, cos 90 is 0. How much I'm going to get? I'm going to get k lambda d. If I take it common, if I look at this, I'll be getting how much? K lambda by d itself. So the E net in this direction will be how much? K lambda by d, and this was also how much? K lambda by d. So if I look at the final result, the net electric field should be K lambda by d and this K lambda by d. Okay, so basically E parallel minus E1 came as negative. It means the net electric field in this horizontal should have been in this direction, isn't it? That's how much? K lambda by d. K lambda by d, and this upside K lambda by d. K lambda by d. So these are the electric field. So the net electric field E net at this particular point should be in this direction, and that should be root 2 times of K lambda by d. I hope you guys have understood this one, right? If you have any doubts in this, do let me know. I'm sure you guys have understood this entire problem, how to handle the questions based on this. Okay, let's see some more example. Okay, take one more example over here. Let's assume that I have these 4 finite wires arranged in shape of a square. Let's say the charge on this is density is lambda coulomb per meter. You can have lambda coulomb per meter over A as well. Let's say negative lambda coulomb per meter and negative lambda coulomb per meter. So these are the charge density. Let's say the side length is A and A. Now my question is, find the electric field at the point joining the diagonals of this square. Okay, so let's say these are the diagonals of this square. I want to find the electric field at this particular point P. That's okay. Now what we can do over here, guys, let us understand the direction of electric field over here. Now because of this, we'll be having one field in this direction, E perpendicular, and one towards left or right, whatever you can choose. Let's say towards right we have. Okay, and okay, no right, because it will be nullified. Let's have a look at this thing. If I assume this side, let's say AB, CD. Okay, let's assume this wire AB over here. Understand this properly. This is, let's say, AB. This point, if I join this, it should be falling at the midpoint of line joining, line AB, right here. If it is A, this length should be how much? A by 2. So this distance is A by 2. Fair enough. So if I want to find the field over here, and this distance is A by 2 and A by 2, then the one going to be E perpendicular, and the parallel component will be nullified, isn't it? So there won't be any parallel component over here. So we'll be having only E perpendicular because of this wire. All right. Now because of this wire also, we'll be having E perpendicular in this direction, E perpendicular. Now let's try and denote the negatives with the blue color. Because of this negative charge, the field should be again in this direction. That also going to be E perpendicular. Because of this, the parallel should be nullified, and then we're going to have one more in this direction, because this, that should be again E perpendicular. So exactly what I'm going to find over here, I'm going to find this net electric field and these two, and I'm going to get the sum of that, vector sum of that. All right, then let's start doing it very quickly. Okay, let's just get this part quite cleaned up. All right, then where is the duster? Okay, anyways, duster is just lost. Anyways, let's try and find this E1, that E perpendicular, this one. Well, that should be how much? K lambda over d times of perpendicular sine theta 1 plus sine theta 2. Well, theta 1 theta 2 all should be how much? 45 degree. So no problem with that. I'm going to have 1 by root 2 plus 1 by root 2, which comes out to be how much? Root 2 k lambda by d. I'm sure it's okay with all of you. Well, this should also be how much? This E perpendicular should be same. So if I look at this net field over here, so let's suppose this is going to be the net field, E perpendicular, or let's say EY, I'm choosing EY, and this is, let's say, EX. Then guys, EY should be how much? 2 times of E perpendicular because of the blue and this black one. So this is going to be how much? 2 root 2 K lambda over D. Okay. Now let us try and find the field in this direction, that is in X direction. Okay. So I can write Ex should be 2 times of K lambda by D. This thing, it's again going to be same, the magnitude going to be same, 1 by root 2 because angle is 45 plus 1 by root 2. So I'm going to have how much? Same thing, 2 times of root 2 K lambda over D. Okay, now let us put the value of D in both the cases. D should be how much? Over here A by 2, here also A by 2. So if I put it that way, I'm going to have how much? Let me, D by 2, D is going to be A by 2. So I'm going to have 4 root 2 over A K lambda. And this again is going to be how much? This is my equation 1. Alright. And this again is going to be how much? Because D is A by 2. I'm going to have 4 root 2 K lambda over A. So I got the value of Ex and Ey. So the net should be nothing but, because both are equal, so root 2 times of, both are equal only, so root 2 times of how much? This net field. So let's find that. So let's say this is E net. So E net should be root 2 times of this value, which is 4 root 2 K lambda over A. Well, that should be 8 K lambda over A, and that's going to be the net electric field at this point. And the direction is very okay, simple, along this diagonal, because both the values are equal. So this angle should be how much? 45 degree. Fair enough. So once we understand that how the field is probably dependent on the wire, it could be infinite, could be semi-infinite, could be probably a finite wire. We know how to choose the angles, we know the formulae, and we know how to decide the direction of the parallel components basically, because essentially the perpendicular components is quite simple. It's going to be away or towards the wire based on the charge, nature of the charge density. If it is a positive, it's going to be away. If it is negative, it's going to be the closer in towards that, right? So now by this time, I think we have done enough amount of questions based on this, and I'm sure you guys are clear with the concept of this electric field due to the wire and infinite wire, of course. Now the next thing which is left is due to finite sheet. Probably we can just talk about that disk. So I would actually combine them together in the next lecture, and then I'll be moving to the dipole, which I'll try to finish in the next lecture itself. And the next going to be your potential energy, potential, a relation between the potential and electric field, and we're going to see some questions on that. And then we're going to move on to the Gauss laws, and we're going to check, we're going to see that we're going to be able to do all this stuff quite easily with the Gauss law. This wire we can do easily with the Gauss law. Alright then guys, okay, let's see one more question before I end up this lecture. Where is my duster, man? Okay, let us try to do one more question. Yeah, since I have put in almost all the part of this electrostatic, I have introduced SHM. So let me finish that rituals over here as well, and let's try and check one question on SHM with a straight wire having charge density lambda. Alright guys, fair enough. I'm sure you have seen those questions where we have found the time period of oscillations happening. We know what is the stable equilibrium, unstable equilibrium. We have seen such questions. Alright then, let's say the next example. Let's say if I have probably an infinite wire, okay, having a charge density of lambda coulomb per meter. Okay, let's have a charge over here Q at a distance of, let's say, D from this wire. Let the mass of this charge is M. Now the point is, if I shift this charge to a small distance, let's say X over here, and then release it, do you guys think it's going to execute an SHM or not? Let's understand this. What happens over here? Okay, it is very important to make sure that it's make clear that at D this charge is in equilibrium. This charge is in equilibrium. That is very important to mention over here. Equilibrium means at this point, because of the field will be upward, the force of gravity will be pulling it down, it's balanced. Means at this point it is in equilibrium, it's not falling down or neither going up. So at this point, let's say at D, this charge is in equilibrium. Now if I shift it slightly, that's what has to be mentioned very clearly, shifted slightly upward by distance, by let's say x, and then released, find the time period of the oscillation. Okay, simple. If I just pull it a bit up towards up, the electric field intensity will decrease, right? Because we know that because of the infinite wire, just now we've done that. Due to an infinite wire, E perpendicular is how much? 2 times of k lambda by d. If I increase this d, the field will decrease. So if it comes over here, the field will decrease, but mg remains constant, which is gonna pull it back towards the ground, right? Towards the downward. And then if it comes down at this particular point, mg will remain same, but the electric field force will increase. Again, it will be pushed upward, right? So in this way, it keeps on oscillating. If I increase this distance to a huge value, it will not be in SHM. So that's the reason why we do say the word slightly. Okay. Now let us try and figure it out. At equilibrium, we need to understand this point. At equilibrium, mg is downward. Let's see this body, mg is downward. The electrostatic force that should be acting upward, F electrostatic, that should be how much? E into Q, that should be 2k Q lambda over D. At this point, they should be equal. So I can say that 2k cube lambda by D is going to be equals to mg. Let's keep this as equation 1. When shifted slightly up, okay, let's do it in this part. When shifted slightly up by x. Now let's see what's going to happen over here. In this situation, mg will remain same, no problem with that. Now this is a charged particle. Now the electrostatic force Fe is going to be how much? 2k q lambda over d plus x, isn't it, guys? Okay, so if it is shifted a bit up, this is going to be the net electrostatic force. So at this point, the net force acting on this, F net, should be how much? 2k q lambda over d plus x minus your mg. That should be the value of the net force acting on that, isn't it? Now we know that 2k q lambda over, if I just solve it from here at this particular time, let us try and take out d common from here. I'll be having 2k q lambda. If I take d common, I'll be having 1 by x over d minus mg. Now if I look at this part, 2k q lambda over d is nothing but your mg. So can I just write this is nothing but mg? I take out common, I'm gonna have 1 by 1 plus x over d minus 1. I hope you guys are okay with this, right? Yeah. Now can you just clean a little bit up over here? I'm sure you guys have noted down the question. If not, you can pause and go back. Probably that's the best part of this recorded videos, So let me have this space over here. Now, so if I try and solve it, I'm gonna get F net is going to be mg taken out common, no problem. I'm gonna have 1 minus x over d, and denominator will be having 1 plus x over d. 1 will be nullified, I'll be left with mg negative x over d denominator I'll be having 1 plus x over d. Okay guys, what you can see over here, let's try and cancel the d. I'm gonna have negative mgx by d over d plus x over d can be nullified, leaving me with negative mgx over d plus x, right? As I know that x is very small compared to d, so can I just ignore this x over here? We know that d is greater than x. Then can I just say this part, your f should be negative mg x over d. Let me rewrite it as this way, negative mg over d times x. If I look at this and do the comparison with minus of kx, I'll find it that the value of k is how much? Mg over d. So from here I got the value of k as mg over d, and we know the time period should be how much? 2 pi under root of m over k. So that should be how much? 2 pi m over k is how much? Mg by d. So mg, d will go up, so I'm gonna have 2 pi under root of t by g. So finally I have actually reached to the answer that the time period of this oscillation should be, the time period, okay, let me write here itself, the time period should be 2 pi under root of d over g, right? And we are done with this. So as per the rituals, I have done one SHM questions in this category as well. Well, that's all for today's guys. I'm gonna see you tomorrow probably in the next video, where I'm going to be discussing more questions based on the probably disc will be the next thing, and the ring will have one more questions on the ring. I found some more good questions which I wanted to discuss, but because in the last video, because of time constraint and the power disruption, I could not do that. So the next video I'll be talking about disc, more questions with the ring and the electric dipole. All right guys, thanks for watching, keep learning, and if you get any doubt, do let me know in the comment box. Thank you all guys, see you soon, be safe, bye bye.